Hi, I'm Milad Nasr. I'm here today to talk about our new work, which is called Defeating Deep Neural Network-Based Traffic Analysis Systems in Real Time. I've done this work with my co-authors, Alireza and Amir. We are at the University of Massachusetts Amherst. So we know that these days every application is using encryption in different aspects, and for communication mostly, and most of the traffic is encrypted, and we cannot look at the content of this traffic between the user and the server, or user and different parts of the network to find out information about the users. But the communication itself can leak information about the users, and we can use this metadata from the communication, like timing sizes, to infer some information. And the art of inferring information from these traffic patterns is called traffic analysis. One of the main tasks in traffic analysis is attacking mostly anonymity networks like Tor, and in Tor uses multiple layers of encryption, which helps to protect the anonymity of users. But the pattern of the traffic in a Tor connection is not perturbed. So if you look at the connection from the beginning to end, the same pattern is preserved. And the Tor is designed to be low latency, so an attacker can use this pattern to do some inference on the traffic. And so there are many traffic analysis systems on Tor or similar anonymity networks. And these days, main state-of-the-art traffic analysis methods are using deep neural networks, and it's been shown that these work can, like using neural network, can improve the accuracy of the detection or like inferring information significantly. For example, we ourselves showed that the traffic correlation on Tor can be improved significantly by using deep neural networks, or website fingerprinting, which is another approach of traffic analysis, also is being improved significantly by using deep neural networks. But we know that neural networks have a main issue, which is they are vulnerable to small changes to the input, and these kind of malicious inputs, also known as adversarial examples, where like if you have a neural network which can identify different images by changing small amount in the pixel values, or adding a small noise to the image, the kind of neural network can change its prediction completely. Our goal in this work is to understand if a similar like adversarial example can be applied in traffic analysis system. Can we use those approaches, or how we should use such attacks on the traffic analysis systems? The problem is that we cannot just use the same approaches, which are like mostly in vision or different application as is, and apply them on the traffic analysis system, because the data for these traffic analysis methods are from the network patterns. And one issue is that if we want to actually use this adversarial example, we have to change the pattern of the traffic in the real time. And there are several issues with that. Many of the adversarial example techniques use you look at the input and decide what noise to add to the input. This is not feasible in a realistic setting for traffic analysis, because you cannot buffer the whole traffic flow and then add noise to it and then release it, because the connection is not gonna wait for you will disturb the connection. So, and also like if you have to add the perturbation to each packet in a real time and very fast. You cannot change the timings of the connection very much. And also one other, so we have to create this blind adversary who doesn't look at the exact traffic flow, and he should perturb the packets in a way to fool these such systems. Another issue, which is also very challenging to apply these an adversarial example for traffic analysis systems, is that many of these protocols in the network have a specific timing or their direction. You cannot arbitrarily change the direction of the like a packet, or just change the size. Like you cannot make a packet smaller because you will disturb the connection. And all of these protocol specifications, this should be preserved. And this will make the applying adversarial example in traffic analysis very complicated. So in this work, we will try to solve this problem by creating a generic framework for applying the blind adversarial perturbation on traffic analysis systems. And to show the possibility of such systems, we created a pluggable transport for Tor, which we call it Blanket, and we also showed the effectiveness of this work on several traffic analysis methods. To find the smallest perturbation such that for every input, which is like traffic flows, the output of the target model will be different when you apply the perturbation compared to when you don't apply the perturbation. And also, by applying this perturbation, the traffic flow shouldn't validate some constraints, which are usually like time constraints, could be a dimensionality constraint, or packet sizes, protocol constraints. So we have this general framework which take care of all of these things. And in reality, when we want to actually implement this, we will use a neural network to generate such perturbations. In the first phase, we will start by creating a set of perturbation on direction, sizes, and the timings. Then we try to make sure that these perturbations don't change the traffic that much and doesn't violate the traffic constraint, as I said, like timing. And that finally we use this set of perturbation and apply and give it as an input to our pluggable transport, and we actually implement it in the real world to change the timing of the packets. So this is the overall view of the work. The setup for this example is, for example, we have a Tor client and it gets packets from a browser like Firefox or a Tor browser, and the packets will go to the a general like architecture in Tor is that the packets from Tor client go to the pluggable transport. Now in this pluggable transport, we will change the timings and sizes of the packets and add either dummy packets to the traffic based on the output of the previous section to modify the to fool the traffic analysis systems and encrypt the whole thing and send it. And at the Tor bridge, we get the packet decrypted and remove the all of the modification that we add to the packet and send it to the Tor network. So this is the general setup. So we evaluated this system on several different tasks like deep core bar CNN and website fingerprinting method, which both var CNN and website fingerprinting is the same, work on like this task. These are the state-of-the-art works on these traffic analysis methods. And we saw that, for example, for deep core, if you don't do any perturbation, the performance is very good and it can easily correlate the packets from the like going to the Tor network when it comes out of the Tor network and can like de-anonymize the network. But when we apply these perturbation based on this system, the performance of this deep core will drop significantly, and the like traffic correlation methods such as deep core, which are using the neural networks, are vulnerable to this type of attacks. Also, we see the same thing here in website fingerprinting. Both DF and var CNN are vulnerable to this sort of. For example, if we want to make the attack to target a specific website and every flow to make this traffic analysis system to misclassify every flow from that specific website, we can also do that with this type of attacks, which is not in the previous works. And we can show that if you can easily, like with small amount of perturbation to traffic, you can make this system to misclassify the inputs. So there are some works in machine learning literature that try to prevent the adversarial examples, but most of them, even in machine learning literature, doesn't work that well, and almost all of them are fail in practice. And we also evaluated all of the state-of-the-art works in machine learning literature, and also we came up with a better version which is aware of the specific attack, and we showed that even when we use the this defense to countermeasure this sort of adversarial perturbation, it's still like when comparing with no defense with our defense, which is the better than all of the existing works, even still there is a huge drop between accuracy of the model, and it's pretty hard to protect against these sort of attacks. And also, we are not the first to try to counter the adversarial traffic analysis methods. We are the first to use adversarial examples specifically in this way, but not like there have been several works on this area, and we show that for example, VAR CNN is pretty robust against the different defenses in this system. But we show that our approach is much more effective, and it has a much lower overhead on the traffic. To conclude, we created a generic blind adversarial perturbation for traffic analysis systems. We applied it for different settings as we wanted to, and we also implemented it in a real world, which we can get it from our GitHub repository. And thank you very much for listening to the talk.